So again, welcome. Time passes very, very fast. We are now already at week 5. Next week is week 6. Then after that is recess week. And then your E-labs also start. So time passes very fast. Okay, 6 o'clock, let's start. Okay, so again, welcome everyone. As usual, let's start by doing the revision review. In fact, I go back actually to a summary of the materials from lecture 3. Right, so recall in lecture 3, we started posing the problem of adaptive control where there was only input-output measurements, right? So we began to set up the structure, right? First of all, writing the system in this differential operator form, right? As we said, so essentially here, equivalent to the pole polynomial of degree n, zero polynomial of degree m, we pull out basically this number out here, Kp, so that the leading coefficients in both of these are just one, called monic polynomials, right? So we also define relative degree, which is just n minus m, right? Then we use the well-known identity, which basically says, all right, you give me a polynomial t of degree n, you give me another polynomial of degree n star, I can kind of decompose it like that, right? Okay, so once we have that, then we said, okay, we use this, right? Back in the original system that we began with, which is the system, then we operate throughout by the EP polynomial. Right, if you look at this carefully, the EP will be monic of degree n star. All right, and most important, as you try to work with differential operators, you need to be very careful. All right, that here this will work indeed with linear differential operators, and they should be time invariant differential operators. Right, so once you have that, no problem. I can operate it on both sides by EP. Right, then I rearrange, it becomes like this, rearrange again. All right, here at this point, noting that this F polynomial is of degree n minus 1, not monic. All right, then here E is monic, ZP is monic, but KP is down here. All right, so we can call this as the G bar polynomial. This is of degree n star, this is of degree m, added together, this whole thing will be of degree n, all right, and monic. Okay, so now if we begin to look at how this whole thing comes about, all right, in particular, what we do is we operate on both sides by a 1 over t filter, all right, and also linear, time invariant, right? The moment you want to operate with a 1 over t filter, straight away, a constraint comes in that your TP needs to be Hurwitz, right, stable. But that's not a problem, as you saw. TP is a design polynomial that we will choose, all right? So that's not a constraint. So we need to go ahead and operate on it like that. All right, we pull out the KP, okay, pull out the KP. So this now, instead of F becomes F bar, but no problem. In any case, this was non-monic to begin with. Then this G bar down here is of degree n and monic. This is also of degree n and monic, so we know that we can break it out like this. So this will be 1 plus G1 over T. G1 will be of degree n minus 1, and now not necessarily monic, right? So now we can write it out like that. All right, write it out in full like that. The G1 will be the G1 polynomial of the G1 Pn minus 1, G2 Pn minus all the way to Gn. The F bar polynomial, also of degree n minus 1, F1, F2 to Fn. Okay, most important at this stage is to see that these are actual numbers G1, G2 to Gn, so n numbers down here, another n numbers down here, that if you go backwards to how we began, all right, we began with the system we're trying to control, okay? And this has basically the n degree polynomial, all right, and this also the m degree polynomial, all these numbers in there, all right, all these numbers in there and the kp. So if it turns out like in your normal, right, in your normal control module, all right, in your normal control module where you are working with a system that you know, so all these numbers are known, including kp. If you take it from the stage that all these numbers are known, including kp, all right, and then you come to this stage and you are the one that will specify the design polynomial t. You are also going to be the one that specify the design polynomial Rm. All right, it will turn out to be a reference model polynomial. So again, well, at this stage, you don't need to know it's stable, but never mind. Okay, in the end, it will turn out to be stable. So TP is chosen by you, Rm is chosen by you. If you knew exactly Rp, you can calculate all the numbers in E, you can calculate all the numbers in F. And then you go along, all right, with all these numbers known, you go and check carefully that by the time you reach this stage, all right, based on the fact that, okay, if you start with the system and if you assume you know the system, and since T is a design polynomial that you choose, Rm is a design polynomial that you choose, after you go ahead and proceed with the calculations, all right, at this stage, you will see that you can exactly calculate out this n set of numbers, G1, G2 to Gn, this second n set of numbers, F1, F2 to Fn. Okay, so you can exactly calculate it, all right? So as I mentioned, I mean, in your CA1, all right, I actually asked you to do this, of course, specialized to second order system. So you see that in your CA1, all right, you can exactly calculate the relevant numbers here, all right, for your simulation, because it's simulation, and you can go and check, all right, how your adaptive system will perform. Okay, so that's the first thing. Okay, so basically, if you knew the system exactly, all these are numbers you will calculate. Okay, then we say, okay, we rearrange, all right, and we see that this can be rearranged to be like that, all right, pulling out the KP, and we said, okay, now if all this whole set of terms in this curly bracket, all right, if it is possible somehow to set this whole set of terms in this curly bracket, all right, to be exactly equals to some k star r, to be exactly equal to some k star r, all right, where k star is essentially defined as kp k star equals to km. Km will be something we will choose, all right, coming out of our reference model. All right, kp is from above. All right, so basically this is completely possible, all right, completely possible because this is at the moment just stating the existence of these numbers, right? So certainly you can set kp k star equals to km, all right, in this manner, and then you put this whole thing in there. If you can set this whole thing equals to k star r, all right, if you set this whole thing equals to k star r, then all right, with this side, all right, if this whole thing is set equals to k star r, then basically you have kp k star, all right, kp k star. Okay, so this now will turn out to be Rm operate on y equals to kp k star of r, which is km of r. Okay, so remember how we've set it up to this stage. So this condition is also there, all right, as part of the development. Okay, so it will become like that. So now remember what was the main thing that we then had to do coming out of lecture 3. We then say, okay, so this is what we want to do now. How does this happen? Right? We said, how does this happen? Okay, so we said, fine, let's see how it's possible to happen, because basically what it boils down to is, right, you take this whole thing, you want it to be exactly equal to k star r, so we write it up. All right, exactly, it basically, if you pull this over to the left-hand side, this you're setting that curly bracket equals to k star r. So what this says is that, look, you know, you really should be somehow generating for me a control law like this. All right, you really should be generating for me a control law like this. And if indeed you can generate a control law like this, then perfectly what you're getting is that, all right, when you generate like this, perfectly you're now getting out of that perfect control law that you're now getting this as the closed loop. All right, which is what will work out nicely for us. So this is now what we can attain if we can set up this perfect control law. Okay, so remember what we then said was, okay, how to set up this perfect control law, how to make sure that it is even something realizable, right? Okay, so I said, okay, not difficult, because now in order to see how this comes about, all right, basically we can look at it clearly. All right, we can look at it clearly for a second order case. And the moment we look at a second order case and we understand it, you can see how it scales up and specializes to the general case. So we say, okay, let's look at the nth order case. All right, let's look at the nth order case. And for the nth order case, what we do is we'll take, okay, we have to choose the TP polynomial. So, okay, let's choose some CP polynomial has to be stable. All right, for now, at this point in time, you know, all that we need to do is to choose TP to be of order n. So n equals to 2 down here. We choose a second order polynomial. And it has to be stable. That's all there is to it. Except that in your CA1, you know, when you actually work with the system now, of course, you know, how you choose your P polynomial will affect the performance. It will not affect the stability. Okay, stability and convergence is guaranteed. All right. But even though that's guaranteed, I mean, you can get some very slow adaptation and slow convergence, or, you know, with a clever choice, all right, you ensure the correct signals pass through, then you can get better performance. All right. So, but at this stage, all right, just in terms of stability and convergence, the only constraint down here is that your TP has to be an n order polynomial and it must be Hurwitz. That's all. So you choose this to be Hurwitz, which means that I can set up a 1/t filter. Remember, you told me that the output can be measured. So I take the output and pass it through the 1/t filter, right? And then the signal that comes out, I will call it Y superscript F1, right? And then what happens down here is that, okay, this is a second order filter, which I can set up in state variable form. So I'll set this up in controller canonical form. All right, I set this up in controller canonical form. All right, if I say in controller canonical form, okay, it will come out like this. Y is coming in. All right, I set up the 1/t filter in this way. Then two signals come out. All right, two signals come out out of this system. All right, and these are the two signals I will use. Okay, similarly, you told me U is also measurable. Okay, that makes sense because, you know, you are going to be the person generating U. So of course you can just take the U and again similarly pass it through a 1/t filter with the same kind of constraints involved. The only thing needed is T needs to be stable and of order n. And it's the same T. It is exactly the same T. All right, so you take the U, pass through the 1/t filter. All right, and then again you set up in controller canonical form. All right, so you get these two signals coming up when you set it up in controller canonical form. Okay, so now you have this. And then you can now see that, all right, for the perfect control law, all right, if you look at it carefully for the second order case, F/Ty comes out to be like this. And it will be F1 times this first signal, F2 times this second signal. And you see that this first signal and this second signal are exactly available out of your state variable realization of the 1/t filter. Exactly down there. All right, you take the Y pass through the 1/t filter set up in controller canonical form, you exactly get these two signals. All right, so these two signals are there. You exactly get these two signals, all right, which is what you want. This is coming out of your state variable filter. All right, you are not separately taking this signal and then differentiating it once. You are not. This is just notation. All right, this is already, both signals are already available in your state variable filter. Okay, so you just basically take it from your state variable filter. These two signals are available. All right, similarly for the U, the filter with U, all right, the out for the perfect control law, you need G1 times the first signal, G2 times the second signal. And again, these two signals, you go and check, are exactly available already in the control canonical form 1 over T filter that you set up with U as the input. Okay, these are the two signals. Okay, no additional differentiation. All right, so these are exactly the two signals you have multiplied by G1, G2. And I emphasize again, all right, if you exactly started off with knowing the system, F1 can be exactly calculated by you, F2 can be exactly calculated, G1 can be exactly calculated, G2 can be exactly calculated. If you started out by saying you know the system. All right, so okay, this for second order system, you see all these signals are there already. So this would be your perfect control law. All right, if you wanted this perfect control law, then I say, okay, let's now make sure that indeed everything is realizable. Let's patch it up properly in a diagram. So in the diagram, all right, you are telling me you want to control the system. All right, your output is measurable, your input is measurable. So here, exactly based on what you told me you want to do, I set up a 1 over T filter for Y in control canonical form. I get out the two signals as you saw. All right, these are the two signals coming out of your state variable filter. Okay, you take U, pass through the 1 over T, set up in controller canonical form. All right, and again, these are the two signals exactly available coming out of your state variable filter. Okay, so they are there. Okay, now I said, look carefully again. So for your perfect control law, as I said, you know, if you knew the system exactly, you can calculate exactly this number F1. You can calculate exactly this number F2. You can calculate exactly this number G1. You can calculate exactly this number G2, right? So here, out of your perfect control law, you see from above, it says that to set up your perfect control law, you take F1 multiplied by this first signal, you take F2 multiplied by this second signal. You take G1 multiplied by this first signal, you take G2 multiplied by this second signal, and you add this K star times R. So let's see. So we exactly do that, all right? We take first signal multiplied by F1, second signal multiplied by F2. First signal multiplied by G1, second signal multiplied by G2. Okay, we put it in with a minus sign, of course. All right, then K star times R, exactly. All right, so under the situation whereby all these numbers can be perfectly calculated, all right, you will see that this diagram exactly realizes for you that perfect control law that is demanded. All right, so it's completely possible. And as I said, you know, you can see this is realizable, this is implementable, because in real life, all right, this system you're trying to control, you're putting an input into the system, you can only measure the output. All right, in real life, you will simply, in real life, okay, you will set up in real time LabVIEW, okay, because in LabVIEW, okay, LabVIEW, you can set up this state variable filter, you can set up this state variable filter, you tap from your Y signal, you tap from your U signal, put this into LabVIEW, and LabVIEW will certainly generate this first signal, the second signal, first signal, second signal for you. Then in LabVIEW, you multiply by these gains. All right, then this is your reference signal you have. In LabVIEW, you multiply by this gain, and in LabVIEW, you sum this up, put this in. This exactly realizes for you your perfect control law. So certainly this is realizable. Okay, so this is clearly realizable. All right, and clearly these numbers exist because if you knew the system perfectly, you can calculate out these numbers, and these numbers exist. Okay, then remember what we said. We said, you know, okay, since these numbers exist, but all right, we're trying to control this and we don't know the numbers, all right, in the system. But we know the structure now. We know the structure that numbers exist to, all right, to perfectly get the job done, all right, if we need it. Except we don't know, because we don't know this, therefore we don't know these numbers too. Okay, if we don't know these numbers, you saw our philosophy, which we developed very carefully, right? You saw that, we developed it very carefully. We said, okay, this is a structure which works. But if you don't know these perfect numbers, you put in time varying gains, right? You put in time varying gains. Okay, you put in time varying gains, and the moment you put in time varying gains, you have to tell me how to adapt them. And this then gives us a structure for adaptive control where only input-output measurable. All right, so clearly we already have a structure now at this stage for adaptive control with input-output measurable, except we haven't reached the stage at this point of how to specify the adaptive law. Okay, so be very clear at this stage, you know, we already have this. Okay, very, very important is that up to this stage, all right, it doesn't depend on relative degree. It doesn't depend on relative degree, okay? Even though I specialize it to the case with order n equals to 2, but you can well imagine, all right, if this is of a general order n, this is of a general order m, all right, everything will still be correct. You will set up a 1 over t of order n, and n signals will come out. You will set up a 1 over t of order n, and n signals will come out. K star r you can generate. All right, and then what happens is that the numbers f1, f2 to fn, g1, g2 to gn also exist. All right, and then these n signals you multiply by them, these n signals you multiply by them, feed them back with the negative sign k star r. And that also exactly implements for you the perfect control law for this system if it is of order n. No constraint on relative degree. Okay, I emphasize no constraint on relative degree at this point. Huh? No constraint at all. Okay, okay. Now go on to additional properties to be observed out of here. Okay, and even at this point, no constraint on relative degree. Okay, so okay, perfect control law, you can write it out, all right, and even write it out in basically a row vector of gains, all right, and a column vector of all the signals you have. These are all the signals you have. You generated them. These are the n signals coming out of the 1 over t filter with y as input. These are the n signals coming out with of the 1 over t with u as input plus k star r. All right, just that I've conveniently written it like that. All right, basically compactly, and it's exactly the perfect control law except written in this manner. All right, and you can see these are the set of perfect gains that if you knew the system, you can perfectly calculate them. These are the set of signals that we have. We have. Okay, here, these are the set of signals, n signals generated with y coming in through the 1 over t filter, n signals coming in with 1 over t with u as the input signals. So these are all signals which are generated by you. So in line with the notation that we've used, the omega set of signals are all signals which you generate. All right, and these are perfect control gains that you are able to calculate if you knew the system perfectly. So these are the theta star gains. All right, so these are the theta star gains. These are the signals that you generate. Okay, so certainly perfect control law can be written like that. All right, and as I said, you know, if you go in and begin to kind of write that further, okay, we can actually use it. So the question now is how to generate the adaptive law. Okay, so as I said, to generate the adaptive law, in this diagram there, which is very, very important, all right, I said, you know, look at this diagram, examine it very carefully. In this diagram, okay, there are some very important properties embedded in this diagram, okay? So before we go on to the adaptive law, okay, let's observe what these properties are, all right? Okay, the first property, okay, we summarize as proposition 1. So remember, these were the n set of signals generated with the 1 over t filter with y as the input. Then these are the n signals generated with the 1 over t filter with u as the input. So there are 2 n signals. All right. So the first set of property to observe, very, very important, is that, okay, it's signals which we generate, but very, very important, it turns out that these signals that we generate actually have a very important property. They are 2 n signals, but when you compose them as a state vector, like as a vector like that, a vector of signals, 2 n signals, it turns out that these 2 n signals as a vector is actually the state vector of a realization of your system to begin with. All right, so basically what is happening here is that this is your system. All right, this is your system. It is of order n. It is of order n. System is of order n. You generate n signals coming out here. You generate n signals coming out here. So n signals here, n signals here. This system is of order n. But if you take n of these signals and another n of these signals and you put them together in a vector, these 2 n signals, proposition 1 says, exactly form a state vector of your original system to begin with. Okay, then you also have to be very clear, right? This is an n order system. Now you tell me you take these 2 n signals put together in a vector, they form the state vector of this system. So clearly it's a non-minimal realization. Okay, so it's a non-minimal realization, but never mind, that's still correct. All right, that's still correct. So these two end signals actually form the state vector of a non-minimal realization, right? As I mentioned, I said, you know, this is not difficult to prove because the moment you claim this is a state vector, you must be able now to go back to the original system and write it in state variable form. All right, so the proof of proposition 1 just requires you to work and carefully arrange it so that you now get that state variable realization. All right, as you do your CA1, I told you there's a very, very detailed file, all right, for your CA1 to help you write your report by my earlier GA, Dr. Sun Lu. All right, you will see down there that in Sun Lu's file, all right, he has carefully shown you, all right, actually the proof of proposition 1 specific to n equals to 2 system of your CA1. All right, so Sun Lu has shown you all the details on how to prove this in his detail one. Certainly I leave it to you to work through it. I mean, that's interesting work to do. All right, it's related to your CA1 anyway, so you should work carefully at it and understand it. All right, and whatever is done there generalizes to the nth order system. All right, so that's not difficult. Okay, then, as I also told you, go back and stare at this diagram now. Okay, so this is your original system to begin with. All right, this is your original system to begin with. And then, you know, you say, okay, in order to generate my adaptive controller, I need to make a 1/t filter here. I need to make another 1/t filter here. And n signals come out here, n signals come out here. All right, and you told me that these two n signals actually form a state vector of the original system, except it's a non-minimal realization. But never mind, it's still correctly a state vector. So all these signals are state variables of the system of a non-minimal realization. So if all these are state variables and you multiply them by numbers, and then you feed it back, as I said, you know, so what is this? You take state variables and all that's happening here is all these are just state variables, that's all. All these are state variables and you're multiplying them by numbers. If you take state variables and multiply them by numbers and feed it back into the system, okay, from your 5101, and as I said, you don't even need your 5101. Even in my undergraduate module, I already teach it. You take state variables, you multiply by numbers, and you feed it back into the system. That's state feedback. That's state feedback. And very, very important, state feedback does not change the order of the system. So here, these two n signals, all right, form a 2n order non-minimal state realization of the system, and you're doing state feedback in the 2n order non-minimal realization, then the state variable system that you've set up remains at 2n order, all right? And state feedback doesn't change the order of the system. So that means that system remains at 2n order even after your state feedback, all right, in the 2n order system, which means that out of your state feedback, there must be 2n poles because order of the system didn't change. So where are the 2n poles? Okay, that's proposition 2, which is an equally important result, all right, which we need to observe. The 2n poles are all there. All right, the 2n poles, if you go, and again, this is also in Sun Lu's detailed report, all right, related to your CA1. It is very much part of your CA1. I would want you to carefully work through the material in Sun Lu's detailed report to help you write your report and to be very, very clear about these two intermediate results there. So the 2n poles are there. And what happens is that when you do the state feedback under the 2n order non-minimal realization, all right, you can go and check, carefully work it out. The 2n poles are now at TP, R, ZP. Okay, you can double check. TP is of order n. Rm is of order n minus m. This is of order m. N minus m plus m is exactly n. So these are where the 2n poles are. TP is chosen by you because you set up the 1/T filter. RM is your reference model, will be chosen by you. So certainly, all right, this part of it is not much of an issue because these are design polynomials and you will choose them to be stable. So no problem at all. But in the way that we are working in this system, the ZP is a constraint we have to live with in the way that we are working in this system. All right, because the 2n closed loop poles are also at ZP. ZP is the set of zeros of the system, which means that this approach is constrained to work with systems with stable zeros, the so-called minimum phase system. All right, as I said, next week we still have a final class with me. I will briefly mention how, all right, with some methods we can handle so-called non-minimum phase system. So we'll wait until next week. But for now, never mind, we live with this constraint. But with this constraint, we can get very powerful results, all right, which guarantees you uniform stability in the entire state space. All right, no matter where you start, it's stable in the entire state space and also guarantee you convergence of the tracking error. Okay, so we have that. All right, using proposition 1 and 2, all right, we can go on further. Okay, now in this case, going on, okay, again, I want to emphasize come up to proposition 1 and proposition 2 results does not depend on relative degree. It works for any system of order n. Okay, so up to here, no constraint on relative degree. Okay, then next, when we try to begin to do a first version of an adaptive controller using strict positive realness, this is where relative degree 1 begins to come in. All right, so proposition 1 and 2 does not need relative degree 1. Okay, it's not constrained by that. It works for any nth order system, any relative degree. Okay, but for the case of the n order system, if we want to develop the adaptive controller, all right, we can note these things. Okay, that you set it up. This is what you set it up. Okay, this is your reference system. All right. This now will be strictly positive real. All right, it turns out that you can actually use this particular adaptive law. All right, where adaptive law, okay, remember, instead of the perfect control gains, we put time varying gains in there, and we will now adapt the time varying gains as theta bar dot of t equals to minus signum kp. Gamma is any symmetric positive definite matrix. Omega bar, remember omega bar is the set of signals, n signals with y going into the 1/T filter, then another n signals with u going to the 1/T filter, then omega bar because we also put the r in down there, so it's 2n plus 1 signals. And the only thing that you need down here is just the output tracking error, which is y minus yn. All right, and then with all of these, assuming that your system is constrained to be relative degree 1, all right, it turns out that we can prove this very, very powerful result that, if you adapt it in this particular way, okay, then it turns out that, okay, similarly as before, right, you can guarantee that all the signals in the system, all right, even though it's non-linear now, it's a non-linear system, there's danger, as I mentioned, of finite escape, but there's no danger down there because with the way we are doing it, we can guarantee that the signals are bounded for all time. So you can actually see those signals for all time. They may be large, but they will never be infinity because, they are bounded, okay? I mean, a large signal, basically a bounded signal can be large, all right? As long as it doesn't zip away to infinity and you can't even see the signal. Because in nonlinear systems, it can happen, okay? It zip away to infinity and you can't even see the signals anymore, okay? So we can show that this is preserved, and we can also show that tracking error goes to 0. Okay, so this is one of the most important parts, all right, that essentially has come out of our lecture number 3. As I told you, I said basically this diagram was the very important diagram ending at the end of our lecture 3. Okay, let me, I'm going to push on with all the revision, all right, of what we did last week. This is actually the earlier week with some from last week, but most of it's from the earlier week. But never mind, I will still do the revision of what we did last week, all right? But at this point, let me pause because even then, this is a lot of things down here. Let me pause and check. Anyone has any big worries or not? And any thoughts, any comments or not? Okay, so far so good, huh? Okay, so far so good. Okay, so as I said, proposition one, all right, up to above here, okay, up to above here, all right. This diagram, okay, control law, proposition one, proposition two, does not depend on relative degree, okay? Only you can work it out for any system of order n, all right? It's only when now we want to first develop a first situation of adaptive control, all right? And one version which is very clear, all right, that's why I also chose it for your CA1, because it's very, very clear. Today, I'll mention what happens when relative degree is greater than 1. All that happens is that you have to do a lot more signal processing now, okay? I mean, you know, then it just becomes, you know, a lot of tedious work. But never mind. But basically, to show the principles of adaptation, that's why I want to concentrate on relative degree 1 first, so that you get a chance to see it, and you get a chance to see very clearly in your CA1. All right. So it turns out the adaptive law will be like this. Okay, maybe let me back off a bit more. Let me back off a bit more. All right, and go back to okay, exactly how we had set all these things up. So remember, we had set all these things up. It's exactly the same, right? So remember, I said this was the diagram, and I told you, I said, you know, have this diagram very clearly in your mind, because many important properties are there, right? Even though it's specialized to second order system, but the general properties are still relevant for a general n order system, right? So I said note that. Then, you know, there's the perfect control law, right? Perfect control law, and then after that, you can rearrange it very conveniently in, right? As you saw, very, very conveniently in basically a row vector of gains and a column vector of all the signals that we are using. All right, then of course, you can go ahead and put it in, substitute it back into the equation, right? Because basically what happens down there is, right, in the perfect set of equations, that's exactly what we're doing, right? What we're doing. And then, of course, what you can do now is noting this, and then if you rearrange that, you can see that now what happens is that, okay, there's theta bar star and theta bar. Okay, you can collect them together, all right, and put a phi down there, all right, then the k star r down there, and you can rearrange that, all right. So this is from your perfect control law, and this part is the perfect control law. This part is the perfect control law. This is the u that we are putting in, right? U that we're putting in, because this is how we're putting in u. Right, so this u we are putting in, this is the perfect control law. So if you rearrange, all right, you can see that the parameter error comes up, the k star is down there. All right, this is now exactly in the system. All right, then reference model is what you set up. All right, then, okay, let me make it just so that we can see. All right, so now you can just take this thing, all right, and in operator form, just take this equation minus this equation. All right, and you will see that this now leads to the error equation coming out like that. All right, with E1 being y minus ym, and that's just the output tracking error. All right, and then it will be the reference model polynomial operator RMP operator on E1 equals to KP phi bar transpose omega bar. Okay, and again, this does not depend on relative degree. This does not depend on relative degree, because up to this point, all that you're saying is that, look, you know, that's my perfect control law. All right, that's my perfect control law. And then I can write it like that. And then in the system, okay, right, this is my U. This earlier part there is the perfect control law that I want rewritten in this particular way. And if I rearrange, it looks like that. All right, and then basically now I have this particular equation, all right, in differential operator form. RP, the RP polynomial operator on Y equals to KP, phi bar transpose omega bar plus K star R. Then my reference model, all right, is also in this differential operator form. The RP polynomial operator on Ym equals to Km times R, and I just can, you know, very directly take this equation minus this equation, because at this point in time, my polynomial operators are all, okay, linear time invariant differential operators. Okay, so I take this minus this, all right, and it exactly comes out to be like this. And this is the equation I will work with. All right, so at this stage also does not require relative degree equals to 1 or strict positive realness yet. This is just arrangement of the whole thing so that we can proceed with adaptive control. All right, so this equation comes up. All right, and as you recall what we said, okay, now, okay, for the first time to begin to show, okay, some adaptive controller, which is something which can be directly seen quite easily, and for which you can really see the adaptation without getting lost in the huge amounts of signal processing. All right, so, okay, if it's the case of relative degree equals to 1, all right, then adaptive law turns out to be rather simple, all right, in the sense that because we can appeal to strict positive realness, and then adaptive law comes out like this. Okay, comes out like this. Okay, then remember what we did last week. Okay, the bulk of what we did last week was to say that, okay, if indeed we look at the case with relative degree equals to 1, all right, and reference model comes out to be strictly positive real, and then it does turn out that we can use this very direct type of adaptation and still get these very powerful results. So the bulk of what we did last week was, okay, so we claim we did this. Okay, let's show it. Let's show it. So that was the bulk of what we did last week. Okay, so this next stage of the revision, I will go to this next thing down here, which was the bulk of what we did last week. And I'll do it carefully again, because actually up to week 3, lecture class 3, in some ways the ideas are there, and even the derivations involved not too difficult lah. But last week was probably the most headache, so I'm going to do it very, very carefully. All right. So with that, let's go on to what we did last week. Okay, last week. Okay, this was last week. Right, where we said, okay, now consider specifically the case with relative degree equals to 1, where right, the adaptive law now for the system, right, because relative degree equals to 1, you have to set up your reference model with relative degree equals to 1, all right, and your adaptation will become like this. So this is the adaptation that you will use. So remember what we said last week was, okay, now show us that the result is exactly according to what was claimed, all right, and it was also completely summarized, you recall, at the end of the set of nodes, the first set of nodes on the system. Okay, you set up this n set of signals passed through 1 over t, n set of signals passed through 1 over t, all right, and then with the r, this is what it is. So this part of it did not depend on relative degree equals to 1. This part of it is what you would do for a general n-order system anyway. But the moment you use this adaptive law, all right, relative degree 1 comes in. And remember what we said was that, okay, it was guaranteed that all signals in the system are bounded and tracking error was guaranteed to go to 0, which you will be able to, you know, explore and really see in your CA1. Okay, so that's why to me is quite exciting, all right? Without all the very messy signal processing coming in. Uh, um, okay, let me don't jump ahead of myself. Okay, so let's go back now to what we did last week and do it one more time very, very carefully. Okay, at this point, maybe I should mention, because I told you last week, because in your minds, of course, in the end, your CA1 coming up in recess week is important. Your CA3 coming up in recess week is important. Then, as I also said, next week, I've told my GA to come at the beginning of the class, next week's class. So I will introduce them to you. All right. So next week, you will just see them for the first time. So next week is Friday, week 6. But the CA1 and CA3 ELAB sessions are in the recess week, which is the week after next week. So it's still good for you to at least see them for the first time. Then when they lead you on the ELAB, all right, on Monday and Tuesday of the recess week, at least you have familiarity with them already. So I've coordinated with them. You will see them at least for an introduction next week. All right, that's the first thing I said. Then remember last week, as I also said, okay, for your grading, there's CA1, there's CA3. Then of course, in your mind, there's also exam lah. So, Prof. Ho and I, we are working on it. Last week, we hadn't fully decided. Okay, this week, I can tell you already because we've discussed and certain things are clear. Okay, listen very carefully. Listen very carefully. So, as we told you, exam will be in person in a classroom venue in NUS. Okay, that will be told to you ahead of the exam. So it will be in person, all right, in a classroom. Okay, exam will be closed book, but everyone is allowed to bring in one A4 page, double-sided of any notes that you want to write. Okay, so remember, it is one A4 page, double-sided. Okay, don't be too clever and say, all right, one A4 page double-sided to make it easy for yourself. And you go and bring two A4 pages and you only write on one side because in the physical exam, okay, apart from Prof. Ho and myself who will be there will also be an administrator who will be there who will also check all of you. And it has happened in the past. All right, some student, more cleverer than what we said, bring in two A4 sheets, single-sided. Then the administrator said, hey, the instruction is one A4 sheet. How come you got two? You decide which one you want to tear away and pass to me. Wow, and so never mind now. But fortunately, the administrator was willing to listen to us. So I said, never mind. Okay, what I do is I take the two A4 sheet and I staple them together so that it's two sides. Okay, because to be fair to the administrator, okay, you put two A4 sheet, single-sided, you have the advantage over other students in the sense that you don't have to waste time to flip and flip. So that's also fair lah. But I said, don't try your luck. That time the administrator listened to us. Okay, if we get another administrator that refused to listen to us, and then you have to give up one of your A4 sheets, I tell you, it will be very traumatic. So remember, okay, it will be closed book, one A4 sheet, double-sided of anything that you want to put in. Okay, so that's the first one. Okay, then remember, I also mentioned that I would think over on this stability analysis for strict positive real part, all right, whether it will be in your exam, all right. Okay, I thought over. It's not difficult. It's not difficult. And basically, once you follow through today, I'll carefully do it. And then, related to it, you would have worked carefully in your CA1. And then you would have looked at Sun Lu's very full written version. And you see all the additional material in there. And we really want you to gain familiarity with that. So I think, with that in mind, okay, I can tell you, okay, this stability analysis for relative degree equals to 1. I'm not saying it definitely come out. What I'm saying is that, okay, certainly, okay, it can be considered for examination. all right, for both 5104 and 6104. Okay, so you better be familiar. Okay, with that, let me push on. Let me push on. So remember, last week what we did, we said, okay, now we had claim, right? We had claim, as I said, that if you were doing adaptive control with only input-output measurable for relative degree equals to 1, this is how you set up the system. This is how you set up the adaptive law, right? And then if you set up in this particular way for relative degree equals to 1, we said that the result is that, in the entire state space, no matter where you start, as long as you start with a finite point, all right? A finite point can be huge, all right, huge, but it's still finite, okay? You can start anywhere you want, all right? And then along these lines, all right, these results are guaranteed, all right? In the entire state space, globally, all right, system remains bounded and tracking error goes to 0. Okay, so let's prove that as we did last week. Let's redo that. So, okay, remember what we said? Okay, remember what we said? This is system given to us. Okay, from proposition 1, the signals that we generated, all right, form a 2n dimensional non-minimal realization of the system. So if I take the 2n signals, all right, first n signals is the y signal passed through 1 over t, generated n signals, and the second n set of signals is u passed through 1 over t, all right, generate n signals. If I put it in there, this 2n order vector, it is a state vector of a non-minimal realization of the system. All right, if I say this is a non-minimal realization of the system, all right, what it says is that this is a state vector. I would take the u, all right, this is the same u. I would take this y, is the same y, all right, and if it is a state vector, I must be able to write my system exactly like that, all right, where the triple from the system polynomials, all right, from the state vector realization must come up, right? As I said, this will come up from your proof of proposition 1, all right, as I said also in Sun Lu's detail write-up, and this is also what you will do in part of your work to carefully do these things as you work with Sun Lu's detail write-up, sample write-up. You will actually see for your second order system, you will exactly see what exactly this AP triple bar looks like, what exactly BP triple bar looks like, what exactly CP triple bar looks like. All right, this is not, as though these are something very strange. These are things which are very, very exact, when you work with the exact system. All right, you will be able to put them down there. So from proposition 1, these things are down there. All right, control law is like this. All right, which we can rewrite it out, all right, as the perfect control part plus the error, all right, even the R part, the perfect part plus the error, all right, and then as we said, okay, so this is how the system is written, all right, in the non-minimal realization, all right, and if we substitute all this control law in, all right, we substitute this control law in, all right, substituting in those perfect gains down there, all right, and if you put the perfect gains, all right, you put the perfect gains, and then you put the perfect gains down there. All right, when you put the perfect gains down there, okay, you already saw from our earlier analysis that when you put these perfect gains down there, these are 2n gains, all right, and this is the 2n order non-minimal realization. That when you put the 2n gains, this exactly comes out to be your reference system. All right, if it exactly comes out to be your reference system, this will be your AM triple bar, this will be your BM triple bar, and this will be your CM triple bar, okay, plus those error parts, all right? And you can double check, because if you exactly put in the perfect control gains, then the errors will all be 0. This will be 0, this will be 0, you can strike this out. Then it will be exactly just AM triple bar, BM triple bar, CM triple bar, all right? And under this perfect gains, you must completely recover your reference model. Okay, so as I said, from proposition 1 and 2, or proposition 1, 2 tells you why all the additional 2n poles are, all right, so basically it collapses to exactly the reference model. All right, what that then says is that, look, what that then says is that this AM triple bar down here, this BM triple bar down here, this CM triple bar down here, if you knew exactly those numbers, all right, if you knew exactly those numbers, you can write it out. Or you can write it out, and basically what this says is that the reference model can also then equivalently be written in 2n order non-minimal realization. Can also be written in 2n order non-minimal realization. Okay, and this will be exactly AM triple bar, BM triple bar, CM triple bar. Okay, so very, very important to know. Okay, okay, then all of these are there, but what is very, very important is to note, as I mentioned last week too, I said, look, this is telling you that conceptually, this is completely possible, because this is how you will set up your reference model, right? You take the reference signal coming in, then it generates your reference model output, all right? But because of what we've seen in propositions 1 and 2, it says that, look, you know, underlying there, okay, there's an underlying 2n order non-minimal realization of the reference model too, because it comes out from your exact theta star gains and your k star gains. All right, so these things are there. But, all right, even though conceptually this is correct, I remember I told you very clear, to be very clear, I said, okay, you need to be very clear, all right, conceptually this is there, but this tells you that all these things exist, but unfortunately, this is not a state variable reference model system. In state variable form, all right, you can set the reference model in input output form. This input output form, this one you can set it up. In fact, you will set it up in your CA1. You will set this up in input output form. It has an equivalent state variable form. Unfortunately, even though this state variable form exists, you cannot set it up. All you know is that it exists. All you know is that it exists. You are not able to set it up. All right, because you do not know the numbers in the original system, and therefore you do not know this AM triple bar, BM triple bar, CM triple bar, even though they exist. And this is a big difference then, all right, from lecture 3. All right, this is a big difference from lecture 2 and lecture 3. Okay, so therefore, even though you know this state variable system, 2n order non-minimal realization of your reference model exists, unfortunately, all that you know is that it exists, but you cannot set it up. All right, you cannot set it up. Okay, but never mind. Even then, we can still use it for analysis. All right, we can still use it for analysis. So we still can say, okay, I'm interested in the state tracking error, which is the from your 2n order non-minimal realization state variables. You have this. This is the n signals from the y pass through 1 over t filter, n signals from the u pass through 1 over t filter. So this set of signals you have. This set of signals, all right, you know exists, but you don't have. But it doesn't matter. It doesn't stop you from conceptually saying, okay, in the analysis, it's important to consider the state tracking error. All right, so conceptually, you can still consider a state tracking error. Then you say, I'm also interested in the output tracking error, y and ym. Of course, this one you have, you can measure y, you can measure ym, so you have the tracking error. Okay, so we say these are things of interest to us. Okay, then we go on carefully. All right, remember this is how we've been able to rewrite. All right, rewrite the system after we have substituted in the perfect control law. Right, this was from above. Okay, this was from above. Once you take this, right, once you take this, this one, okay, taking the, right, this part equals to AM triple bar, BM triple bar, CM triple bar with these errors down here. Take this part, 3.1, all right, and take this conceptual realization, 3.2. So take 3.1 minus 3.2. You take 3.1 minus 3.2, all right, you will be able to get this equivalent error system. All right, so should be familiar to you, all right, because bears some similarity to lecture 2, all right, bears some similarity to lecture 2. So conceptually is like this, okay, conceptually is like this, okay, except that be very careful to note, all right, be very careful to note that we already know that if you put in the perfect control gains down here, you put in all these perfect control gains down here, you get AM triple bar, you get BM triple bar, which is here, you get CM triple bar, and exactly this AM triple bar, BM triple bar, and CM triple bar, this triple, all right, this basically, this triple of matrices, AM triple bar, BM triple bar, CM triple bar, is exactly the state vector realization of your reference model. All right, but be very careful to note that the rest of the error terms come out like this. All right, the rest of the error terms come out like this. So basically track it very, very carefully. Whoops, I may have. Okay, correct. Okay, be very clear that, okay, this is how it comes up. And take 3.1 minus 3.2. Right, when you take 3.1 minus 3.2, you will then begin to see that, okay, what then happens is that this BM triple bar, all right, this part, of course, gets away. Then you are now left with these two things down there, which we will carry. All right. So remember, okay, it is BP triple bar. It is BP triple bar down here. If you track that carefully, AM triple bar, CM triple bar down there, and this is BP triple bar. This BP triple bar because you see this on BP triple bar. Okay, but you also know that BP triple bar is related back to BM triple bar as K star BP triple bar equals to BM triple bar. So now we will rewrite it in terms of BM triple bar, which is now how the 1 over K star comes out when we put back the BM triple bar. Okay, so be very careful. All right, be very careful. So now note that we have AM triple bar, BM triple bar, and CM triple bar. Okay, and we already know that this triple of matrices, AM triple bar, BM triple bar, CM triple bar, are actually 2n order non-minimal realization of the reference model. But this is AM triple bar, BM triple bar, CM triple bar. You got to take a note that there's a multiplier 1 over K star down here. Okay, so we note that. Never mind, we note that, and we begin to carry on. So we collect together the 2n plus 1 error terms. Then 2n signals down here, put the R down here, it also becomes 2n plus 1. All right, so we label it as omega bar. Okay, note the 1 over K star. So now this is how the system looks like, right? With the BM triple bar brought in, but the multiplier 1 over K star must be down there. All right, and the thing to note down here is that in here, if I just take AM triple bar, BM triple bar, CM triple bar, all right, if I take that already, I know this is KM over RMS. Okay, because we already know that AM triple bar, BM triple bar, CM triple bar as a triple of matrices, all right, forms a non-minimal realization of my reference model. So this is perfectly correct. All right. And then, of course, you know, specialized to the case of relative degree 1, as a transfer function, this is strictly positive real. All right, so this is strictly positive real. Okay, then recall that for relative degree equals to 1, all right, we said adaptive law can be like this, right? Okay, so let's check how the adaptive law works out. Okay, let's check how the adaptive. So let's again look at this ellipsoid function. All right, and then now from Kalman-Yakubovich lemma. All right, Kalman-Yakubovich lemma say you go back, all right, go back to your system, okay, to begin with. This system is strictly positive real. Okay, so you go Kalman-Yakubovich lemma, the stability matrix down there in the first place obeys the straightforward Lyapunov equation, AM triple bar transpose PP, AM triple bar equals to minus Q essentially, but can be decomposed more finely in this way, but essentially equals to minus Q, that's the first part. But also remember that, okay, for a strictly positive real system, you can say more. You can say more because what happens down there is that, okay, for the P that you calculate, all right, you take the BM triple bar and the CM triple bar, it is now also additionally related, which we will use. Okay, so now let's go ahead and begin to do this from E dot, all right, from E dot above, okay, go and check E dot above. So from E dot above, we already saw that this should be like this with a 1 over K star multiplier. So exactly, we put that all in, put it all in, put it all in. All right, so this first part we already know equals to minus E transpose QE. Then this second part is down there. Okay, this second part is down there. Okay, recall from earlier. All right, recall from earlier, I think this is here. All right, when we were carefully setting up the system that, okay, one part of the condition that had always been down there, all right, which will come back to be needed to be used again. Right, that in your reference model, okay, see this? So after you set up the perfect control law, this part comes up. All right, this relationship comes up that KP K star will be equals to KM. Okay, okay, don't worry, we will make sure that everything that we do is proper. All right, everything that we do is proper in the sense that it does not violate any requirements and directly take knowledge from the system. No. All right, so basically KM equals to KP K star is part of our setup down there. Okay, so now minus E transpose QE is down there. All right, that part is sign definite. It is that part that we want. So we still are left with this second part. All right, let's carefully check this second part down here. Okay, sorry, I should have put triple bar. Forgot. Okay, this is BM triple bar. This is so, but there's the multiplier down there, 1 over K star BM triple bar. Okay, so this is down there with the multiplier. Okay, never mind. So KM over RMS. So now if you need me, because of how the error equations have come out, there's the multiplier down there. All right, never mind. So I will still stay with my reference model, which I have to set up. So KM I know. RMS I know because this is the reference model that I set up. Okay, this is the reference model I set up. KM over RMS I know. So I set this up completely. Now in my analysis, multiplier 1 over K star comes up. Never mind. So I will take 1 over K star, put it in here. But since I don't know the sign of K star, I just multiply my reference model equation by 1 over magnitude of K star. If you take a strictly positive real transfer function, you multiply it by a positive number, it remains strictly positive real. Okay? It remains strictly positive real. So to begin with, this is my reference model. Relative degree equals to 1 is strictly positive real. All right, I multiply it by a number. All right, 1 over magnitude K star. I will not need to know the value of 1 over magnitude K star. All right, all that I need is, this is what I set up. Okay, this part I need to know because I need to set it up. But if I multiply this by a positive number, this remains strictly positive real. So all that happens is that, all right, I'm still looking at AM triple bar, BM triple bar, CM triple bar. But now since it becomes like that, okay, I put in the multiplier 1 over magnitude of K star. But it remains strictly positive real. So since it remains strictly positive real, the Kalman-Yakub-Borish lemma equation still hold, this part still hold. And the P that I calculate, remember from Kalman-Yakub-Borish lemma, it says, okay, now you take this P, multiply by whatever B vector is in here. So my B vector here, okay, has the multiplier 1 over magnitude K star. I just put it over there. Will now be exactly equals to CM triple bar. That's from Kalman-Yakub-Borish lemma. All right, that's from Kalman-Yakub-Borish lemma. So I say, okay, this part down there. So I go back now. All right. So remembering this part as well from the earlier part. All right. And what will happen, of course, in the way that we will set it up, reference model, we will set in a straightforward way, because look, you know, there's no sense in trying to say put KM equals to negative and have your system turn the other way around. So straightforwardly, KM will be a positive number. So you choose KM to be a positive number. If you choose KM to be a positive number, all right, if you choose KM to be a positive number, which you will, all right, then since KM equals to KP K star, whatever is the sign of KP will also be the sign of K star, because KM is positive, all right? Whatever sign of KP is, if KP is positive, K star has to be positive. Otherwise, KM, you know, does not maintain the condition. So if KP is negative, K star will be negative, right, to maintain this thing. And KM is what you choose, right? What you choose, and essentially, okay, you will choose KM equals to greater than 0, because basically it also makes no sense, all right? I mean, to choose it negative, because strict positive realness will require you to just make this positive anyway. All right, but you also basically, look, you want the motor to turn positively when you put a positive input. That's what you want, right? You don't want to be perverse anyway. Okay, so now note this part of it. So whatever the sign of K star is, it will be exactly the sign of KP. Okay, now go back to how our equation came out. our equation came out to be like this. For Kalman-Yakubovich lemma, P multiplied by BM, P multiplied by BM with the additional multiplier 1 over magnitude of K star was exactly equals to CM triple bar. Exactly, this is from Kalman-Yakubovich lemma. All right, this is from Kalman-Yakubovich lemma. So exactly equals to CM triple bar. Okay, and then you go back and look at your error equation. All right, you go back and look carefully at your error equation, which is here. Okay, this is CM triple bar. But CM triple bar transpose of your state error vector is exactly your output error. It's exactly your output error. Okay, so this is why we will put the whole thing to good use. All right, because we will now say, with all of this, with Kalman-Yakubovich lemma, all right, now this is CM, it's E transpose CM, but E transpose CM, that's a scalar, you can change it back to CM transpose E, all right, it will be E1. So this is E1, this will be E1, all right, this will be E1, okay. And then basically, all right, you saw signum of K star and signum of KP is the same thing. All right, so you can now see that, okay, what happens down here is that basically this will be minus signum of K star. All right, this is signum of K star, okay, all right, and this is minus signum of K star. When you go and double check it, okay, these two terms exactly cancels out, leaving you with the sign definite term from which we can then systematically now get all the properties which we have carefully analyzed in our signals and system, signal by signal before. All right, this is completely what we had done. All right, completely what we had done up to last week's class. So I've carefully reviewed it again. And again, to remind you, okay, exam will be in person at a venue in NUS, which will be told to you definitely ahead of the exam itself. For the exam, it will be closed book. You can bring in one A4 page double-sided. Remember, it's one A4 page double-sided, okay? And then I also told you, I said this part, all right, on Kalman-Yakubovich lemma. Okay, you don't need to know the Kalman-Yakubovich lemma. All right, but here, this is simply using the Kalman-Yakubovich lemma. All right, so this is certainly for this part, it's also relevant, completely relevant to how you will work with your CA1. So this will also be part of what is possible for the exam, because last week I told you I wasn't sure yet. So this week I confirm it for you. Okay, let me now pause to start recording. Okay, 7:25, so let's start again. So as mentioned, right, as mentioned, now for your CA1, both for 5104 and 6104, we have set it to be relative degree 1 case. Adaptive law is like this. So in terms of the careful analytical developments, we've shown uniform stability in the entire state space and guaranteed tracking, right? So you will get the opportunity to work on this in your CA1, as well as work out all the details for the second order case, which would make the things very, very clear for you, right? Okay, so that is relative degree 1, right? As I mentioned, relative degree greater than 1 actually is not a problem. It's just very, very messy, right? And you will see, it's okay. This first part, the control law, all right, is exactly the same. All right, it doesn't depend on relative degree, okay? But now, because you cannot appeal to strict positive realness to set up your adaptive law, you will see that a lot more signal processing is required, All right, a lot more signal processing is required. So in the earlier days, I used to force the 6104 people to suffer to do all this additional signal processing. But actually, in the end, after I, read so many versions of report, you don't learn too much more from the additional signal processing. I'd rather you see, how indeed the adaptation happens. So that's why for 6104 people, all right, from a few years back already, all of you, 5104, 6104 people, your CA1, you just work carefully for me on the relative degree 1 case, all right? But later today, you will see in your 6104 work, all right, I will mention that, all right, I asked you to do more in your CA1, all right? I asked you to do more in your CA1 and also in your CA3, but actually it's not just, the method that, I'm asking you to do more. And you will see it's actually not much more, but yet in the so-called additional or more things that I'm asking you to do, I'm asking you to actually think a lot deeper. Okay, I mentioned some of these later on today. So as I said, relative degree greater than 1 is not a problem too. All right, just a lot of additional signal processing. Then again, you can carefully set up the stability properties, and it will also be uniformly in the entire state space, except you have to do it very carefully. All right, break it up in stages. All right, and then in the later part, as the first part, then in the later part, you really have to look carefully at signals and systems. All right, you really have to look at signals and systems. So that's why, I was very impressed when a lot of you all told me you know a lot of signals and systems, so you don't need. So anyway, as I said, these things are all possible to do. All right. Basically, you're looking at ordering of signals. All right. The supremum measure of signals and so on. So this is true signals and systems. Okay, but let me say this. All right. Even though I show this and I show all this complicated signal processing. Okay, so before the break, I told you about the requirements for the exam. So quite a lot of things. Okay, now after the break, let me say this, which will be good news for you, that all this on relative degree greater than 1 stability analysis are requiring you to look at function spaces of signals. All right, basically looking at function spaces of signals. Okay, not needed for the exam, both for 5104 and 6104. Okay, both for 5104 and 6104 for relative degree greater than 1. All right, all the stability analysis which requires basically function spaces of signals. All right, it's all here. It's all here. All right, signals and systems, but no need. Okay, no need. It's quite interesting. So if you have the time, go ahead and take the time to read it. All right, in earlier years, some of the students, not all of them are students, all right? Some of them are not working with me, but they've gone on to read this thing and able to use it even in their own PhD work. So as I said, this is actually quite interesting, but not needed. Okay, not needed for your 5104 and 6104 exam. Okay, I state that very, very clearly. But I want to remind you, all right, there is only this additional part, all right, all this messy signal processing and all these function spaces of signals and all that, all right, that additional part. But insofar as control law, it doesn't depend on relative degree, all right, so this part is correct for whatever end. So this part, don't say, hey, how come this part, can still be relevant. Okay, this part, it doesn't change. Okay, so that's why I said, look, it's the same control law. Okay, and it doesn't depend on relative degree. Okay, so that's the first thing. Okay, let me push on further. So remember, okay, so we are carefully now using strict positive realness, right? Using strict positive realness, carefully work through. As I said, some of this you have to note very carefully that we are using existence ideas. All right, so conceptually it exists, so we are able to use it in the analysis. But you have to note very carefully that the existence of some of these concepts allows us to use in the analysis. But you have to be very clear what is actually implementable and usable. So here, everything that we have done in analysis, conceptual. But finally, when it comes to what we need to do, we are only using really available signals. So you see, it comes out to be like that. And we are able now to completely, as I mentioned, establish all these very rigorous results. Okay, with this, let me again pause here, check whether anyone has anything to say or anyone has anything worried about. Okay, let me again, because sometimes over Zoom it doesn't get across. Okay, let me say again, my student Haoren and Jiahui, I need you all to stay back after this. I still want to talk to you all on a few more things. Okay, can you acknowledge Haoren and Jiahui? Okay, I started. Okay. So, okay, for the rest of you all, okay, anything you all want to mention at this stage? Any worries or anything? Okay, with that, let me very quickly mention that this evening, about more than half an hour before class, what I did was I uploaded Note 05, which is completely written. All right, because actually for today's class, that part of it which pushes on a bit further, it is not difficult. So I don't really want to, in a way, waste the time just to do the right thing. All right, so this is, I uploaded this, everything is completely fully written. All right, completely fully written. And why I say this is, if you now go back to what I said about the stability analysis for relative degree greater than 1. All right, I said, look, it's not difficult to do, except now you have to do it very carefully, breaking it into many parts. All right, and it turns out that, okay, you now have to do the first part. And this first part actually, which I'll mention later, all right, in a way, all right, are things that we also can do. Okay, just that you have to rearrange the signals. All right. Second part is, of course, more difficult, all right, when it comes to function classes of signals, but still it's interesting, all right, I leave it to you all. Okay, so anyway, go back to this part for which the handwriting completely done, which I uploaded because no point wasting time. All right, so if you now begin to look at what is there in this set of notes, number 5, all right, this is completely written now. Okay, some of these things you will now begin to see were things already in there. All right, so sure. All right, we had started off developing these things as adaptive control. But you see, finally, when we began to, after we developed the structure for the controller, when we finally came to various different sets of equations for which we're able to do adaptation, the truth is, actually, when you really want to do very rigorously provable, guaranteed convergence, guaranteed stability, there are actually very few structures which are down there, and we have already kind of rearranged things into them, and they are there. So let me point out to them. All right, and you will see that what then happens is that if you are now able to very intelligently use all of these so-called aerodynamical models, all right, based on them, you can now begin to build on it and handle much more difficult adaptive systems. But basically, they are still built on these very fundamental ideas. All right, as I said, the relative degree greater than 1, it was just a lot of messy things which you have to do many stages. But again, we're basically built on this. All right, even some of the newer work. Okay, so let me quickly mention this. All right, first one, which sometimes it's labeled in some of the books as the error system number 1. All right. When you stare at this very carefully, you will recognize this. This actually came out when we started developing adaptive control with full state variable measurable. All right, even though we were looking at adaptive control with full state variable measurable, basically it brought down to this. It brought down to this, that you were able now to rewrite it like this with a set of signals that you were generating. All right, remember the set of signals in omega were all signals that you generated. Then these were the set of parameter errors. All right, and this was a stability matrix. And the moment you came up with an error system like this, straight away you know that the correct way to pair it with the adaptation was phi dot equals to minus sigma kp gamma E transpose PB omega. Right, and you saw that, okay? As I said, even if you develop further to get rid of this sign of Kp, the rest of the structure still remain. All that you were doing was you were now putting in basically a very intelligent way of handling the control direction, so to say, called the Nussbaum game. All right, we've done some of that in our own work. All right, but basically it will be still this kind of structure. All right, so this had come up from your when we were looking at adaptive control with full state variable measurement. But basically it boils down to this pair of equations, right? So, you know, it comes out like this, and we can say this kind of result. Okay, then the other result that we had, all right, which came out from strict positive realness, all right? And basically, if you stare at it carefully, it was like this. Okay, in strict positive realness, the transfer operator was strictly positive real. Conceptually, you could say many things about what was happening inside this transfer operator, except that you cannot get the signals in there. All that you knew was that this transfer operator was strictly positive real. But the moment you knew this transfer operator was strictly positive real, and if all you get is an output error signal, all right, and again with signals coming in like that, and you go and see, basically what we did today, even though it looks so complicated, boils down to this, right? That you had a set of signals that you could generate and a set of parameter errors that you had, and you were passing it through a strictly positive real operator. Then if you were doing that, then it turns out that, look, you know, it was very simple. You could pair it with this way of adaptation. All right, and based on that, you can again do quite a few other more advanced things like backtracking, backstepping adaptive controller, and even this one, okay, even though we took it from, develop it from adaptive control with full state variable measurable, all right, even though we took it from there, all right, actually you will see that the robotic control equation for adaptive control of the Hamiltonian systems of robotics can be rearranged looking exactly like this. And you can do adaptive control essentially even on your Revolut joint robot once you cast it in this particular form. Right, so it looks like that. Okay, so this was the strict positive real. Okay, and again, this is what we proved. Right, then we started off in lecture number 1. We carefully did all the signals and ideas carefully. But if you stare at what we did in lecture number 1 and redraw it, because lecture number 1 is first order system, and redraw it, you will see that basically, all right, if we already solved the strict positive real system, we didn't have to signal by signal check all this thing out, because this whole thing now basically is equivalent to this strict positive real arrangement. So actually lecture 1 is a special case of what we had done last week and re-summarized today, except that I still feel there's great value in lecture 1 because it's quite important to understand signal by signal what was happening now. Okay, then one last one, all right? One last one, which I say, you know, the relative degree greater than 1, all right? Even though it looks so complicated, all right, but basically what it was using, all right, basically what it was using is even simpler so-called error dynamical model. And sometimes it's even called error dynamical model 0. And it's very simple. This is all they're saying is that, look, you know, again, you have a set of signals that you're generating or you have, and a set of parameter errors that comes out in this way, all right, with some sign coming out in this way, and an error that you can measure. And if you wanted to again adapt this set of parameters, then it turns out that you were paired in this particular way, all right? And even in this simplest one, you will see that the moment, you have a KP coming out down here, the sign of KP is required. And in this pair of equations down here, if you want to push forward ahead in research, all right, this is where the whole idea of control direction and Nussbaum gains actually that solve it came about, all right, which can be generalized to a Nussbaum matrix, all right, it comes out from here. Okay, this one you can actually quite simply, all right, if you want to prove the stability, all right, you can go ahead, all right, as I said, this is very simple. Okay, all you do is you actually look at this spheroid in n space, go and look at it and then differentiate it, you get phi dot, you see it turns out like that. All right, so quite expectedly, all right, and you will see that actually this is used, all right, in the stability analysis of the very, very complicated relative degree greater than 1 case is used here. All right, except we use them very, very carefully, cleverly and stage by stage. All right, so as I said, these things are there, but why I especially want to bring this particular thing up is that, and this is also partly related to, so as I said, some of you have gone away, including my own students, Jiahui and Haoren, they went away quite excited and went to look at some additional things, and in some ways quite clever, some of the things that they did, all right, following along the lines of backstepping, but some things you need to be very clear, because if you now stare at these things carefully, all right, some things will come up, because this is the simplest aerodynamical equation, and yet in this simplest error equation, okay, something is already there. Okay, let me go back to that. All right, as I said, in this simplest error equation, it comes out like this. There's an error you can measure. Okay, there's an error you can measure. Okay, there's a set of signals that you are generating coming out in omega. So there's a set of parameters you want to adapt for which the errors come out like this. So your adaptation comes out in this particular way. All right, your adaptation comes out in this particular way. All right, and as you see from, so today, the one very, very important thing that I want to mention is, you see in this simplest dynamical equation, all right, even the analysis is quite straightforward. It's just a spheroid. You can look at this and you come out, it comes out to be basically, all right, E squared. All right, it basically comes out to be E squared. Okay, it basically comes out to be E squared. All right, and because it comes out like this, again, you can go and look at doing the integration over any period of time, which leaves you with the square integral of E1 squared. And again, you can conclude. Again, you can conclude in this simple one that E1 will go to 0. Again, you can conclude E1 will go to 0. Okay, so E1 will go to 0 even in this very, very simple structure. Very, very simple structure. Okay, so here with this pair of equation, in how you will end up doing the adaptation, your E1, all right, this arrow down here will go to 0. But this is where, even in this very simple one, some fundamental things are already even here. Because even in this very, very simple one, you follow up through the analysis in the way that we've done it, all right, taking the square integral of E1 squared, all right, and following carefully, you will see E1 tends to 0, all right? Because from function spaces, all right, L2 spaces, L infinity spaces, E1 will go to 0, okay? But even in this very, very simple one, even though E1 goes to 0, so this is directly now addressing partly some of the efforts that Jiahui and Aaron were exploring, investigating, partly just for their interest, because their primary research is not in adaptive systems. They're supposed to work on intelligent systems. But anyway, they were exploring this. So here, even E1 will go to 0, okay, in this system. But even though E1 is going to 0, you have no guarantee that phi will go to 0, even though E1 is going to 0. No guarantee at all. All right. So you can go and set up this simple system. Go and set up this simple system somehow. All right. And then go and exploit. Okay, don't take one dimension. Take maybe at least two dimension. So two signals down here. In two dimension, you'll be able to see it already. All right. Okay, you will see that E1, all right, in this pair of equations will go to 0. But there's no guarantee that phi will go to 0. All right. Why is that so? Here, why I want to bring this up is that here is very easy to see. E1 goes to 0. If E1 goes to 0, all that you can say is that phi transpose omega is going to 0. Okay? Phi transpose omega is going to 0. All right, so let's say you have two signals in omega. All right, and you tell me phi transpose omega is going to 0 on a two-dimension plane. On a two-dimension plane, phi transpose omega is going to 0, your two signals. All right, as your two signals are moving about in your two-dimension plane, all right, phi transpose omega is going to 0. All that it says is that, I don't know how your two signals are coming about. All right, I don't know your two signals in omega are coming about. But if your two signals in omega are living in your two-dimension plane in such a way that somehow, even as E1 goes to 0, what will happen is that, because remember, phi is adapting. And what happens is that, and you will find, all right, if you carefully do your CA1, you carefully do your CA3, you will actually find that what is happening is that your phi is adapting and evolving, because phi is adapting, evolving. Omega is a signal coming out from whatever your system is. But the phi is adapting such that on your two-dimension plane, all that happens is that it is moving in a direction finally as you adapt such that it is orthogonal to your two omega signals. And you can well imagine that in two-dimension, if that can happen, if it's three-dimension, if let's say you have three signals and your three signals are somehow just stuck in because you can have three signals, but your three signals can be stuck in a two-dimension plane. Right? Your three signals can be stuck in your two-dimension plane, all right, because your three signals, depending on how they come about, can be three signals, all three signals, but they are stuck living in a two-dimension plane, all right, in three dimension. Then your phi signal, all that happens is that it is staying orthogonal to your two-dimension plane, and your phi signal parameter error can even be very far from 0, okay? And that brings forward that whole idea, all right, which is quite important, that whole idea of so-called persistency of excitation. And it's difficult, it's a difficult concept because in your, okay, let's go back right to the top, all right, where it's also down there. You can see that, these are your omega signals which you generate. But remember, your omega signals that you generate are not signals that you can directly, first signal, you can put it directly wherever you want. Second signal, you can put it directly you want. Third signal, you put it directly. And fourth signal, you put it directly you want. Your omega signals is coming out of some signal that you're putting into the system, and your omega signals are coming out of the system. So you don't have direct control over individual signals for omega, right? Depending on how, you just have to see how it comes out. So therefore, all right, it is the same kind of a situation even in this very simplest error model. That what will happen is that typically how it will boil down to, even though it finally boils down to this, that these signals down here that you're able to use are signals that somehow you're generating, passing through filters and dynamical system, all right? And somehow there's something down there, which now brings up to the whole concept of persistency of excitation, all right? And this is not just words. Persistency of excitation doesn't mean that your signals should just jump about and be non-zero. Your signals can be just jumping about and still living in a two-dimension plane, even though you have three signals. And they're still jumping about, but they're not properly now, kind of spanning the entire three dimensions so that, it is having a projection component everywhere all the time. All right, so that's the concept of persistency of excitation is a very definite, rigorous analytical concept. And it says this: if you tell me you have a set of signals, all right, let's say you have N1 set of signals down there. All right, your N1 set of signals, all right, if you go and double check, all right, and you want to say they are persistently exciting, then the only thing that you have to carefully do, and because these are derived signals, so it's not so easy to show. But anyway, all right, basically the definition comes about like this. You must be able to take your, okay, whatever n1 dimensional signals or whatever, you take your n1 dimensional signals, you go and find for me any unit vector in n1 dimensional, this will be any unit dimension, and you take any period of time. If you claim your signals are persistently exciting, then you must find for me a guaranteed period of time. All right, guaranteed non-zero period of time. Okay, you must find for me a guaranteed non-zero period of time. Okay, it can be 0.01 second, never mind. But it cannot, once you tell me 0.01 second, then every time you go and check this, you cannot drop below 0.01. So you're saying there's a minimum time, all right, whereby no matter where your signals are, you pick up any unit vector in the n dimension, you must be able to find a projection. Only then, all right, will you be able to indeed satisfy this concept of persistency of excitation. All right, so as I said, for 6104 people, even though basically it looks like I'm asking you to do more in your CA1 and CA3, it's not just the more, all right, you will find embedded in there, all right, there are parts of these deep concepts that I want you to explore and then begin to see what is happening down there. Okay, this is all I want to do for this evening. You will see that my approach to handling my classes is I don't want to rush. When I was younger, I used to do that, I jam a lot of things down the class. But, my philosophy now is, okay, I just want to focus across some very, very important ideas which are possible to build upon, all right? And I don't want to jam too many ideas down because no point, all right? Too many ideas, everything gets lost, okay? So the key ideas, all right, but emphasize. Okay, so I'm done. I stopped the recording.